All right. Well, thank you everyone for attending today. Just to introduce myself to those not familiar with me, my name is Chris. I'm currently an honors student doing statistics at the University of Sydney. I guess first off, I'd like to thank Nathan, especially for a lot of input he's given to help me prepare this talk. And funnily enough, this is my first academic presentation. So it's quite a milestone for me, and I'll greatly appreciate any feedback on my academic presentation skills as well at the end of the talk. That'll be much appreciated. So today my talk is going to be on latent Dirichlet allocation in topic modeling. And to give an idea of what the aims of this talk is to give an introduction to the field of natural language processing, and in particular topic modeling, to everyone here, and to give you guys potential ideas to incorporate topic models into your own research, because they are quite extremely powerful models and algorithms that are used in a lot of the machine learning community, and has a lot of applications, as we will soon see in this talk. So there are quite a few subsections in this talk, but what I aim to lay out in this talk is first off the intuition behind what LDA is, and then diving into a bit of the mathematical derivations of LDA, and then how do you actually infer the parameters in the LDA model, and then look at some applications of LDA, what are the drawbacks of LDA, and also how can you then take this LDA, latent Dirichlet allocation, into your own research. So to give a motivation on topic modeling, latent Dirichlet allocation, as you can imagine now in this day and age, we're collecting a lot more data, especially in the form of text, in forms of documents. So suppose that we have a large corpus of documents, such as journal articles or newspaper articles from the New York Times, for example. And currently this data is unstructured, messy. There's no cohesive way to actually analyze it using traditional econometric methods. So let's say we want to be able to analyze the data and look at the structure and similarities across topics. And in particular, we want to be able to see what are the relationship between documents and what are the underlying themes behind the documents. And this is what topic modeling tries to get to, in essence, is that given a large corpus and collection of documents, we want to see what are the underlying themes, or in this case, topics, that underlie across all the documents. And with that, how can we then organize this collection of documents according to these themes and topics? And in particular, you can kind of think of it as like a clustering problem, where you want to create clusters of documents that are related to one another based on these themes. So in essence, what we'll be seeing in this talk and the outcome of LDA and topic modeling is that suppose we have a structure, a large corpus of documents, and that we're interested in looking at how do these documents relate to one another. And in particular, what LDA can give back to you is a list of all the different topics that underlie your document. So for example, here, topic 1, you can see there's a lot of, this one's about technology, so computer, systems, phone, internet, whereas this topic here is more business oriented, sell, product, business, advertising. So you can kind of see what are the themes underlying all your documents. And this is what the models in this talk will give you. So just to quickly give some use cases and applications of where we can see LDA being used again, like I mentioned multiple times, if we want to see what are the relationships and what are the underlying themes behind topics, we can look at this graph, for example, this picture, for example, where you have different nodes being topics, and then the edges between them showing the relationships between different topics. You can also use topic modeling in a temporal aspect as well. So for example, this graph here was generated by running topic models on, I believe it was Science magazine articles in every decade. And from this, we can see what are the topics being written about in science magazines, what are the hot topics in that decade. So for example, in the 1950s, we can see topics surrounding like tube, glass, air. Those are quite hot topics and things that are written about. Whereas in the 2000s, we see a lot more articles being written about devices, silicon, material technology. So this is how you can use topic modeling in a temporal aspect. This is another application of topic modeling where it's for significant event detection, which I believe we had a talk on at Soda Labs previously. And what this is that there was a collection of documents written by embassies in the 1970s to note important political and historical events in the 1970s. And you can run topic models on that to detect what are big topics that have been written about. So for example, here, you can see this point here, which is related to the evacuation of Saigon and South Vietnam. And so topic modeling is able to help pick out big topics that are being written about. Additionally, from a more networks communities approach as well, you can also look at it from a community's perspective. So here, imagine each node is an individual in a society, like whatever that society may be, maybe a school or a village, and the edges shows the relationships between individuals in such a society. And then you can try to figure out what are the communities within a school. So for example, you could have clusters of communities of people by ethnicity or by gender, etc. So again, the topic models can be recasted in a community detection formulation. So given those, I guess, taste of what topic models can be used, let's actually get into it. So what this talk is based on is on two primary papers. The Latent Dirichlet Allocation paper by David Blei, Andrew Nguyen, Michael Jordan in 2003. Another paper written by David Blei in 2012. And the Latent Dirichlet Allocation paper is quite a seminal and important paper in the field of computer science, bringing the ideas of Bayesian analysis into natural language processing.
Please, can I ask you something?
Yep.
We haven't met formally, so we do this online. I have a question for you. So at the beginning, you said something about, so with this modeling, you basically you give topics?
You give documents and you give back topics.
So you don't have to choose and kind of guide.
So that, you're right, there is a caveat in the sense that you're going to have to assume there's a certain number of topics in your documents, but I'll get to that later in this talk.
So you don't choose the topics. You say, okay, here is a list of things. I don't know how to classify them.
Yep.
You're going to spit out for me some topics.
Yeah, that's the beautiful thing.
And unsupervised.
Yep, that's the beautiful part of this, is that it is unsupervised, like you're getting at. That's why it's a powerful approach.
But you can you supervise it?
There might be formulations of it, but I'm not familiar with that, sorry.
Thank you.
Yeah, sorry, just another background information. I just started my honors this month, so this year, so it's only been a few weeks of me reading papers. So let's now discuss what is the generative process that goes behind these topic models for us to then construct our models. So again, here is a paper on genes, right? And in particular, given a single document, we want to find what are the different topics within that document. So here you can see that we highlighted different words in different colors, and the different colors represent different topics. So for example, here you can see that the blue is more computer-based words and computer predictions, numbers, whereas yellow represents a different topic, where it's genetics, sequenced, genome. So that's another topic which is primarily around genes. So given a document, we like to find what are these topics within a document, which is a collection of words. So in machine learning, a very popular approach in machine learning is to first specify something as what is a generative process behind your data. So what that means is that we tell ourselves a story about how the data came about. And in that story, we have lots of things involving random variables and distributions in our building blocks of that story. And underlying those distributions in our generative process or our story are things known as latent variables, which we would then try to use probabilistic inference, try to figure out what are those underlying parameters in the distributions in our generative process. So many times, the key takeaway of the slide is that we're going to assume a generative process for which our data came from. And it's just like if anyone's familiar with maximum likelihood estimate, you assume your data came from a Gaussian distribution, for example. You compute the likelihoods and you solve to find the parameters. Likewise, we're going to assume a sort of process in which our data has come about. And then once we make that assumption of the process, we then try and infer what are the parameters of that process. So we're trying to reverse engineer this generative process. And this is quite common in machine learning. So just to start slowly defining, introducing concepts of this. So the first concept I like to define is something called a topic, as I mentioned many times. And a topic is literally a probability mass function over all the words in our vocabulary. So if we have 10 different words in our vocabulary, a topic will be a probability mass function over those 10 words, where we assign a higher mass to those words that are more associated with that topic. So for example, if our topic was, I don't know, economics, for example, then we might be assigning a higher mass to words such as utility functions, to agents, etc. Okay? So that's what a topic is. And here in this example, you can see in these topics, we have assigned probability mass functions to certain words in our vocabulary. Now we're going to define what a document essentially is in this case. So a document is a combination of topics. And recall that topics are probability mass functions themselves. So it's actually a mixture model. So it's actually a combination of probability mass functions. And that's what a document is. And this matches our intuition that if we have a document, we might expect it to be 80% about economics and 20% about mathematics, for example. And that's where that intuition of a document comprises of, is a way a combination of topics. And in those topics, we have words. So now this, the next definition we're about to introduce, this is something that trips up a lot of people, especially when being introduced to LDA for the first time. So please do ask questions if you don't understand, because it's quite essential for the rest of this talk. But suppose we have a document, an empty document, no words at all. And suppose we have n what we call word positions. So these are n blank spaces in which we can fill words in. So for a given blank space or word position, we can use, we're going to insert a word into that empty position. And from this, we actually now want to populate each of these word positions in our document with actual words. So how do we actually go about populating these word positions with actual words? So first, we pick a word position, so a blank space. And now first, we're going to figure out which topic is this word going to come from. Is this word going to be from an economics topic? Is this word going to come from an English literature topic, from a mathematics topic, etc.? And recall that we said that a document has different proportions of a topic. So this document may be comprising of 80% of economics. And if that's the case, then when we're trying to pick a topic from our word to come from, there'll be an 80% chance the word will come from economics topic. So first we pick a topic from which the word will come from. So here we pick the red topic. Now we pick topic economics, and remember a topic is a mass function over all the words in the vocabulary. So then we look into the economics topic and look at the mass function over all the different words associated with economics. And then from that, we pick a word from there based on the mass functions over the different words in the topic. And hence in this example, this empty spot, we pick the red topic, and then we then look into the red topic, and then we pick out the word mathematical from that topic. So there's a two-step process here. Is that clear for everybody? Any questions on that?
I have a question.
Hi.
Oh, yeah. No, go ahead, Minali.
Yeah. Hi, Chris. I wanted to ask, so what is the aim of this process? What are we trying to do by picking words and placing it in? Is it like reverse engineering?
Exactly, that's correct. So once we're given an actual document with words, we assume this was the process that generated that document, and we want to reverse engineer it.
Okay, cool. Thanks.
Any other questions?
Also one from me. The word mathematical could either come from the economics topic or from the mathematical topic, right? So economics uses mathematical functions, and math also uses mathematical stuff.
That's correct. But the frequency in which it will appear in a topic will differ. So maybe in mathematical topic, the word mathematical will be a lot more frequent or a lot more likely.
Thank you.
Yeah. All right, so that is the generative.
Sorry, Chris.
Sorry.
The topics, are these predefined? I might have missed that. So as you said, let's assume in the first one, that's the economics topic.
Yep.
Are the words in there predefined?
So the actual words in the vocabulary, they're just all the words that could possibly exist. But in terms of the topics, like you've asked, in this generative process, we assume that there exists these topics in this generative process, but later on, in our inference problem, we actually don't know what these topics are, and we're trying to figure it out.
Okay.
So we're trying to reverse engineer.
Yeah, okay.
So this is like all right. Yep, so again, like I mentioned, this is the key thing in machine learning, where you assume a process, and without process assumption, you try to reverse engineer the parameters. So like I mentioned, for each of the n word positions in a document, we pick a topic from which word it will come from. We then look into the topic and we pick a word from that topic. And that's the word that goes into our word position. And we do this n times. So the key inside LDA and how this differs to previous topic modeling approaches is that it assumes that the model will incorporate the fact that every document will have the same set of topics, but the proportion of those topics would differ in every document. And this makes sense in terms of intuition. Like some documents might be about 80% about economics, whilst other documents may be 80% about biology, for example. Like different documents will have different proportion of topics in them. So this is the goal now. So we have assumed the generative process of how our document was constructed by picking topics and picking words from those topics. We now want to reverse engineer the process, because we're now given our documents that we have. We want to figure out for each document, what is the proportion of a topic in that document? But more importantly, we want to figure out what are the topics, like what is their proportion of words within each topic. And that's the thing we want. And that's the thing that we were looking at in the beginning, where we had different topics showcasing different words. So can we infer the topic proportions for documents and topics over words? So before we dive right into that, we just need to quickly make a quick detour on the multinomial and Dirichlet distribution, which is something that will appear quite frequently throughout this talk. So just a quick reminder, the multinomial distribution, which is parameterized by two parameters, n and p, is just a generalization of the binomial distribution. Remember, the binomial distribution, you have n trials. Each trial could either be in one of two states. The multinomial distribution instead is that it can be in one of k states now. So the probability mass function of that is given by n factorial divided by n1 factorial. So let me start again, sorry. N factorial is the total number of states, n1 factorial to up to nk factorial. And we also have another parameter p, from p1 to pk, where p is the probability of something being category k. So p1 will be the probability of being in category 1, p2 will be the probability of being in category 2, and so on. It's just an extension of the binomial distribution. And I guess a quick Example, if we have a die with 6 sides, so we have 6 categories, we roll it 5 times, what's the probability that 3 2s and 2 4s comes up? So we've rolled it 5 times. We said it's going to appear in category 2 3 times and appear in category 4 2 times. And then probability being category 2 is 1 to the 6 to the 3. And the probability being in 4 is 1 to the 6 squared, which gives us 0.001. So that's the multinomial distribution. And keep in mind the parameters are very important, the number of trials and the probability of being in each category. That's very important. And we can also visualize the multinomial distribution, which will be helpful later on. So suppose we only have 3 outcomes, so 3 different categories, and that's represented by each of the corners here. So let's say this bottom right corner is category 1, this bottom left corner is category 2, and this top corner is category 3. And suppose we vary that probability vector of being in category 1, 2, and 3. So let's say for this first triangle here, we set the probability of being in category 1 to 1, and probability of being in other categories is 0. And that'll be represented by this dot here in the bottom right of the triangle. If we likewise change it so that we set the probability of being in category 2 to 1, and everything else to 0, we are now in this spot here. So each dot represents a multinomial distribution, like where it sits between in this triangle. And this is for 3 categories. Likewise, if we set the probability of being in each category, one of 3 categories equally likely, 1/3, 1/3, 1/3, we're in the middle of the triangle. So this visual aid will become really useful when looking at the Dirichlet distribution, which we'll soon see. For those interested, you can also rewrite it in terms of a gamma function. Don't worry about the form of this. But what the key point of this is that there is a strong relationship between the multinomial distribution and the Dirichlet distribution, which is what we're about to see. So the Dirichlet distribution, where the name Latent Dirichlet Allocation gets its name from, is that the Dirichlet distribution is a continuous multivariate density function. It has 2 parameters, k, so that's going to be our number of topics, as we'll see later. So it has one parameter being an integer k greater than 2. And another thing called concentration parameters. So this is a vector of k dimensions, where each entry in that vector is non-negative. And this is the key takeaway and use case of the Dirichlet distribution, which we'll need frequently throughout this talk, is that once you specify the number of categories, k, and you specify a parameter alpha, what the Dirichlet distribution gives you is a k-dimensional probability vector, where each entry in that vector is a probability, and it sums up to 1, okay? And that is what the key use of the Dirichlet distribution is. Again, here is the form of the Dirichlet distribution. It doesn't really matter in this talk on what the actual form is, but that's just for those interested in looking at it later on. And now here is probably one of the most important slides in this talk, and ideas to keep in mind is that the multinomial distribution can actually come from a Dirichlet distribution. So we have a Dirichlet distribution, we can generate a multinomial distribution. Now, how do we actually go about doing that? So recall, in the Dirichlet distribution, it outputs us a k probabilities, right? A dimension k probability vector. If we take that dimension k probability vector, we can then put it in to, the multinomial parameter p. Remember, the multinomial parameter p is what's the probability in being category 1 or 2 or 3 or 4, etc. So you can see here that if we take the output of this k-dimensional probability vector from the Dirichlet distribution, we can use that as a parameter for the multinomial distribution. So just to make that a bit more concrete, let p be the k-dimensional probability vector that comes out from the Dirichlet distribution. And this is going to go into our multinomial distribution. This p will be, what's the probability in being category I? Now, the interesting thing is the connection here. So you see these 2 pictures. So recall the right-hand side, that is the visualization of the multinomial distribution, right? Where if we set the probability of being outcome 1 to 1 and everything else to 0, where our multinomial distribution is on this bottom right corner. Now on the left here, that's the visualization of the multinomial distribution of the Dirichlet distribution. So what I mean by that is, let's say that we set that parameter alpha to be 1 in the Dirichlet distribution. What that essentially does is that it says that every single multinomial distribution is equally likely to come out. And if I set alpha to be higher and higher, so alpha equals 3, in this third triangle here, we are slowly concentrating to the center. And that means that from our Dirichlet distribution, we're likely to get a multinomial distribution that has probabilities of being in each outcome equally likely. Does that make sense for people? Or is there any questions? Because this is quite a key step for later on in the talk. Okay, so taking the output of the Dirichlet distribution, we can put it into the multinomial distribution. And that's how those two are related. And likewise, if we vary the parameter alpha, we can shift around what sort of multinomials are we likely to get out. So for example, in this image here, the first triangle, that means from our Dirichlet distribution, we are likely to get multinomials where there's a strong tendency for outcome 2 to occur. Here, we have a Dirichlet distribution that gives out multinomials where there's a strong tendency for outcome 3 to occur, and so on. So varying alpha, the parameter, we can get different multinomial distributions coming out. So this relationship between between Dirichlet distributions producing multinomial distributions is quite essential for the LDA model. Just to recap what we've done so far.
Can I ask one thing about the graphs on the previous slide?
Yes.
So is the third graph one where a lot of topics are a lot of documents are relatively homogeneous in being either one topic or the other, whereas the middle graph would say all documents are very likely to be of one specific kind, whereas the third graph is one where there are distinct topics, but each and every document is relatively homogeneous in being either topic 1 or 2 or 3.
That's correct. Mm-hmm.
Okay, good, thank you.
And as Sasha noted, that's how we're going to interweave this idea of Dirichlet distributions and our topic models. So to recap thus far, we have specified the generative process in which our data was created. Remember, where for each word position, we pick a topic, and in that topic, we pick a word. And we also have described the Dirichlet and multinomial distribution. So the next step, and the final step really, is that with these two ideas in mind, and also using the observed variables we have, which is the documents, we now want to figure out what are the latent variables. So what are the topic proportions and what are the topics? Just for a bit more mathematical definitions, a word W is defined to be something in a set of vocabulary from 1 to big V, where big V is all the possible distinct words in our collection of documents. So it's just something within the set. A word position, like we mentioned quite a few times, is a spot for a word to be placed in our document. A document D is a sequence of n words. So a document can have n words, and n depends on document. So n can differ for each document. And finally, a corpus C is a collection of m documents. So we have a corpus with m documents, and each document has n words.
Can I ask you one more thing? Right now, you are talking about the sequence here, but still in the probability distributions, as far as I understood so far, there is no spatial dependency. What I mean is the word Chris after the word Sasha and the word Chris before the word Sasha is the same thing in terms of defining a topic.
Yep.
Or do we say Chris followed by Sasha has a different meaning than Sasha followed by Chris?
Yeah,
you know what I mean?
Yes, so that's actually a good point. First, we'll show you how the words are actually generated in a document, but I think what you're alluding to is actually a drawback of LDA, which I'll explain at the end of this talk, but there is no distinction between Chris and Sasha and Chris.
Yeah, or in other words, this is not about n-grams, right?
Yeah,
it's
that's
just
correct.
1 grams.
Yeah, that's correct.
Yeah.
So we've described our observed variables, and now we want to describe the latent variables in our model. These are the things that we don't know and want to infer. So a topic K, so we have K topics. So a topic K, which we denote by beta K for the rest of this talk, remember, is a probability mass function over the entire vocabulary. So in this image here on the left, for this topic, we can see it's a probability mass function over each word in our vocabulary. Next thing we'll define is a topic proportion, which we denote by theta D. And what a topic proportion is, it's the proportion of a topic in a document. So again, going back to our example, a document could be 80% economics and 20% mathematics. So that's what this theta D is. It's like, what is the proportion of topics for a document? Now, finally, a topic assignment, again, which confuses a lot of people in the first reading of LDA. So we'll go a bit slower on this. Let's say we are at the nth word position in document D, okay? We're at a word position. A topic assignment was the process of choosing which topic will a word come from in this position. So let's say we have a blank spot in our document and say we want the topic assignment to be from economics. So the word that's going to go into this spot is going to be from economics. And that's what a topic assignment is. And we denote that by ZDN. So it's a topic for the word position N in document D. Any questions on that? Definitions? Okay. So now we have specified what these variables are, and now we're going to assign where do those distributions we saw earlier of the multinomial and Dirichlet come into this. So, so remember, each topic is a probability mass function over all the words in the vocabulary. And that has a multinomial distribution. So by that, I mean, for a given topic, it has a multinomial distribution over all the words, where it is, what's the probability of having a word in the multinomial distribution. And that comes from the Dirichlet distribution, like we saw earlier. Because remember, a Dirichlet distribution generates multinomial distributions. So a topic is a multinomial distribution, and where that comes from is a Dirichlet distribution. And we have K of these. So we have K multinomial distributions for each topic. Then for each document, so our M documents, we want to look at what's the topic proportions. So is it 80% economics and 20% math? Is it 40% economics and 60% biology, etc.? Again, this is a multinomial distribution over topics, where we have K outcomes for that. So the topic proportion for each document is a multinomial distribution with K outcomes or K topics. And again, that comes from a Dirichlet distribution. The next one is, remember, for each word position, not word, but word position in our document, we select a topic for the word, for what topic would that word come from. So for example, in this empty spot, we need to choose which topic would that word come from. We choose topic red, so we know that this word will come from topic red. And again, we choose that topic for the word position using the multinomial distribution as we defined in the previous step for the topic proportions. So what I mean by that is if this document has 80% economics in terms of its topic proportion, then we have an 80% chance that the topic assignment will be from economics. So now finally, the final step is that we have picked what topic will word come from. Then we look into that topic and pick a word from that topic using the multinomial distribution beta that we defined at the very beginning. And that's how it works in terms of interweaving the densities and the generative process we described. So in particular, the generative process of LDA is that we generate a set of multinomial topic distributions for each topic from a Dirichlet distribution. For each document, we choose the size of the document using a Poisson distribution. For the proportion of topics in each document, so like 80% economics, 20% biology, we construct a multinomial distribution, which comes from a Dirichlet distribution. Then for each of the word positions in a document, we choose what topic will the word come from, and we choose that by the multinomial distribution defined for the topic proportion. And once we pick the topic, we then look into the topic and then pick a word for that. And we'll do some graphical examples of this. Is there any questions on that process? Sorry. So we'll quickly go into something known as graphical models in machine learning. So this might make it more clear, this whole process. What graphical models are in machine learning is a way to link the idea of probability theory, graph theory, and algorithms into one. So we described an algorithm for which we constructed our documents. What a graphical model can do is that it can give a visual representation of what's actually happening here. So, and by the end of this talk, we'll be able to interpret what this graphical model is for the Latent Dirichlet allocation. So here, these 4 nodes in the middle, like this one, this one, this one, this one, each node represents a random variable with an associated distribution. And edges indicates dependence. So for example, this edge from theta to z, this means that z is conditioned on theta. Okay, and that's how dependence is defined. So if you have an arrow coming up from one node to another, that indicates that you can condition it on the previous node. Shaded nodes are observed variables. So here, the shaded node WDN, that's our words in our document that we know because we give the algorithm the documents. And unshaded nodes are latent variables. So here, beta, k. Remember, these are the topics which we don't know. Theta D, remember this is the topic proportions for each document. So it's 80% economics, 20% biology for each document. And ZDN is the per word topic assignment. So for this word position, which topic will the word come from? So we'll quickly go through what the graphical representation of what we just described using this notation. So here, again, in step 1, for each topic, k topics, we draw a multinomial distribution beta k from a Dirichlet distribution. So here, remember our topic is a probability function over all the words, and that's a multinomial distribution. So we generate k multinomial distributions, and that's what this box with the k is. That means we generated k multinomial distributions, one for each topic. Then this box M means we'll do it M times, but for each document D, and we have M documents, we draw a multinomial distribution theta D, and this multinomial distribution theta D is what are the topic proportions for a document. So is 80% economics, 20% mathematics. So we have a proportion of topics for each document for our M documents. Then for a given document, we're now going to look through all the words or the word positions in that document. Suppose we have a document and it's 80% economics and 20% mathematics. Then for each word position in that document, we have an 80% chance that a word will come from the economics topic and 20% chance it will come from the mathematics topic. And we do this n times. And finally, in our final step, we know what topic the word will come from. So we then look into that topic distribution beta k, and we pick a word randomly from that topic. And that's how we generate the final word wn. Is that clear to everyone on any questions on the whole process? Okay. So yep.
Sorry, I just had a question. So when you say we draw a multinomial distribution, so do we just initialize it like randomly and then just, or
so
like can we already preset it, or like how do we draw?
Yep. So remember how we can generate multinomial distributions from the Dirichlet distribution? So to begin with, we have a Dirichlet distribution. We set an alpha parameter, and then we sample from the Dirichlet distribution. And that sample that we got is a multinomial distribution.
Okay, yeah. So in this case, it would be the parameter lambda, right? Like
yes.
But there is no rule like of initializing, like to say, well, lambda has to be 2 or 3 or so.
There is no rule as far as I'm aware. There might be research into what the optimal lambda is, but I'm not familiar with that.
Okay.
I mean, I don't think there is a clear-cut lambda to use to generate multinomials.
Okay, thanks.
No worries. So the good news is that was the hardest part of the talk, and everything else is now relatively downhill from here. So we have 4 variables of interest. We have the variable W, so the actual words we've observed, the variable beta, so the topic. We have the variable theta, so the topic proportions for each document, and the variable Z, which is the topic assignment. So now in terms of inference, this is going to be a short section, just in the interest of time. We specified the generative process and the latent variables of our model, and now we want to infer what are these latent variables, the theta, Z, and beta. So I guess first off, since we have 4 variables, we can define the joint density function of beta, theta, Z, and W. And you can use repeated applications of, I believe it was Bayes' rule to get something like this, but don't worry too much about this problem.
I can see the downhill now.
Don't worry, this is as much math as the remaining of the slides. But don't worry about this bottom line. Just care about that we can write a joint distribution of beta, theta, Z, and W. So all our variables of interest. Also remember, by definition of conditional probability, that the probability of our latent variables, beta, which is topics, theta, which is topic proportions, and Z, which is topic assignment, conditioned on the words we observed, can be written as the joint density divided by probability of the words. Now, the issue is that this denominator here, the probability of the words, that is actually intractable to calculate. Because recall, if we have variables X and Y, the probability of X can equal the probability of X conditioned on Y for all values of Y. Likewise, for this, probability of W is the probability of W conditioned on our latent variables for all possible values of latent variables. And that is intractable to calculate. So unfortunately, there's actually no tractable way to calculate our posterior distribution of interest, this beta, theta, and Z. So I'll quickly point out 2 key techniques used in the field One is variational inference, and another is Markov chain Monte Carlo algorithms of how we figure out what these latent variables are, just a more intuitive approach for those interested. So what the Markov chain Monte Carlo algorithm does is that suppose we have a distribution and it has a density function f that we wish to sample from, but too difficult to sample from. Just in our earlier case, we saw that we couldn't sample, that the probability of W is intractable. Likewise, suppose that sampling from f is not feasible. However, suppose that there is another density function from a different distribution Q, and which we can sample from, and it's somewhat proportional to our density function. So it's kind of like our density function of interest, but we can actually sample from it. Now, what Markov chain Monte Carlo algorithms does is that we can sample from this other density that's easier to sample from, Q, in such a smart manner where the sample points we collect will eventually mirror our density of interest, F. And all the magic and mathematics is in the part of how do you smartly sample from Q to get it to be similar to F. And that's essentially what Markov chain Monte Carlo algorithms do. So in our case, we can sample from a distribution with a density function that's quite similar to the one that we want to sample from in a smart manner. Variational inference is another popular technique used in machine learning. So suppose we have our density of interest, fx, so here it's this red line. And what we can do is we can specify a family or a bunch of density functions that are lower bounds to that our density of function of interest, f. So for example, here we can specify two density functions, this purple one and this green one. And what variational inference tries to do is that we want to pick in our family of density functions, the one that is closest to our density function of interest, f, through optimization and using a kind of like a distance metric, which is called the callback library divergence. And what the callback library divergence does is it takes in two density functions and it tells you how similar they are. So we want to pick the density function that is the most similar through this measure to our density function of interest, f. And then that's how, and then we can then sample from that optimal density function. Any questions on those two different approaches to sampling?
Chris?
Yep.
Yeah, sorry I joined late, but I had a question. So the KL divergence, as I know it, it's not symmetric. So
yeah, so it's not a metric. You're correct.
Right. So does that impact its usage here? Like because we're trying to see if two distributions are identical. So should it matter that I compare X with Y or Y with X in this case? Does it have an impact? I
can't remember the exact details, but I remember that I think the density of interest will be in either first or the second one that goes into your callback library divergence. So you always have to make sure you have the right way around when you're using that.
Right.
So it does matter as well.
Yeah.
So I just can't remember which way to use it.
Okay, no worries. No worries. Thanks.
But what is the logic of this asymmetry? Is the idea that deviations on one side are penalized more than deviations on the other side?
That's a good question. I used to know the answer to that, but I can't remember why the asymmetry.
No worries, no worries.
Yeah.
Thank you.
Yeah, it's been a while. So we're just seeing two different approaches to sampling from the distribution. What are the trade-offs? So variational inference is actually a lot less computationally expensive compared to Markov chain Monte Carlo algorithms. However, a big drawback is that if you specify a bad family of densities to optimize over, you'll get terrible results from that. And so MCMC algorithms, even though they're a lot more computationally expensive, I would say that they're somewhat more robust than variational inference, and also requires a lot less complicated maths to compute. So just some quick applications now of LDA, 2 specific applications. Here in the original paper, they again took, this is for LDA on one single document. So here they took the genes research paper, so seeking lifespan genetic necessities. And here you can see on the left-hand side, the topics that were generated. Here, there's 4 topics. So you can see here in this topic, the words gene, DNA, genetic, and this one, this pink one is life evolved organism. And just a caveat from practical experience as well is that when you get back, for example, this yellow topic, remember, it's going to be a probability distribution over all the words. So you'll have a bunch of words that have 0 probabilities. So you could just drop that. So you could just take the top 10 words with the highest probabilities and define that to be your final interpretable topic. The second example is that here, this left diagram, this left chart, that again looks at the topic proportions in that previous genes article. So we can see here that topic, I would guess that's 20, constitutes over 40% of the topics in that document, whereas topic 88 is 1% of all the topics in the document. On the right-hand side here, this is then fitting LDA to 17,000 articles from the Journal of Science. And here are a bunch of topics that were returned from that process. So you can see here that you're able to figure out what are the key topics in this. And then from that, as a researcher, you can delve further into that to explore. I guess the final, second final key thing is, why does this actually work? Is it Bayesian magic? But there's actually an interesting way to think about why LDA actually works. In particular, LDA tries to trade off between 2 goals. And the conflict between these goals will eventually lead to sort of an equilibrium where the model actually works out. So the first goal is that LDA wants that for each document, we want to assign as few topics as possible to that document. So an extreme example is that LDA would like a document to only have 1 topic in it, essentially. Whereas the second goal of LDA is that for each topic, where recall it's a distribution over words, we want that each topic to be as uniform as possible over its distribution over words. So for a topic, we don't want it to have too much probability for a given word. And these 2 goals actually clash with each other, as we'll quickly go through. So let's look at extreme examples. So let's suppose that we satisfy goal 1. So let's say that in our given document, we only have 1 topic. But the issue now is that in that single topic, high probabilities are going to get assigned to certain words because those certain words don't have any other topics to spread the probabilities to. Now, in the converse case, suppose that goal 2 is satisfied, that we have quite a uniform distribution of probabilities over all the words in a topic. But now when we're trying to assign topics to a document, the document is going to require lots of different topics in order to capture the different frequencies of words appearing in the document. Hence, will require lots of topics. So these 2 clashes between the goal 1 and goal 2 is actually what leads to sort of an equilibrium at which LDA actually gives out nice results. Any questions on that? Okay, so in the interest of time, I've said a lot of good things about LDA. What are the limitations? As noted, first off, a common criticism is the Dirichlet distribution we used in the very beginning. A lot of cases, using a Dirichlet doesn't make sense in terms of the data, and it's a common criticism. Another big thing, which has been alluded to quite a few times throughout this talk, is how do you pick the number of topics K? There isn't quite a clear-cut consensus on that, so that's sort of a hyperparameter you're going to have to use and trial. Finally, as what Sasha mentioned, it's what known as the bag of words assumption. So the order of words don't matter in this model, but we all know that the order of words matter. Like the words depend conditionally on the previous word. And finally, just a quick aside to quantitative linguistics as well, is that LDA does not take into account a lot of statistical laws in linguistics we see. So for example, Heap's law is a law where the number of unique words scales somewhat linearly to the number of the document size. So here on this right graph, we can see as our document size grows, the number of unique words also grows somewhat linearly. And Zipf's law states that the frequency of a word is inversely proportional to its rank in terms of frequencies. So for example, the word that's rank 1 has a certain frequency, whereas a word with a much lower rank has a certain frequency according to this inversely proportional relationship. So the issue is that LDA does not take into account these laws, which we see so frequently in documents, that again, it makes us question whether was this generative process we assume, does that even make sense? So just final takeaways from all this is that if you're interested in using LDA in your own research, R, Python, and Stata has their own implementations of LDA. And to kind of conclude is that what makes LDA such a powerful technique is that it's unsupervised. So you can just feed it a bunch of documents, specify a parameter K, and you get back topics, which the model will figure out for you, which is quite an amazing benefit. Furthermore, with this tool, it allows you to organize the unstructured text document and see what are the relationships between documents and what are the themes behind this collection of documents. And finally, it's an interpretable model because it gives you back a list of topics underlying all your documents. So with all that, that concludes my talk. And thank you all for listening to my first ever talk. Thank you.
Great.
Thanks so much. That was awesome.
Thank you.
Mm-hmm. Yeah, great talk, Chris. Excellent.
I have one question before, and everyone probably is so tired of talks today. But so if I have, you say it is a problem to choose the number of topics, but I could play around with it, right?
Yes.
I specify 6, and then I realize that 2 of them have a very low likelihood. Is that okay?
Yeah, that's fine.
That's what people do, or because I would think, if you find that, I don't know, most of your text falls into math and biology, then having 4 categories doesn't make a lot of sense because anyway, the other 2 topics are very low. I don't know. I'm just asking. I'm ignorant.
No, that's the correct assumption, but you may find that there may be subtopics within maths. There may be different branches of maths may come out of your model as a result. So maybe calculus or differential geometry, etc.
So I don't know if I understand correctly. So you're saying that if I restrict to 2 categories, I might find subcategories that would pop up?
Potentially. I mean, it depends on the data, but I've seen a lot of cases where subtopics comes up and I was playing around with topics.
Okay. Thank you.
No worries.
Thank you very much for the talk.
No worries.
Chris, I had one question left. I was wondering just application-wise. So, I mean, we know that it's a bag of words model. So, I mean, obviously it always depends on the text corpus you will be training it on, but like, is there, I guess there's a literature on, like, does it make sense to consider like bigrams or trigrams? I guess going further doesn't like much. Does it improve it? And I mean, general is always like in machine learning probably not a good word to use, or like to train a phrase model first of all to have like unigrams, but consider some kind of expressions like New York City or something like that.
Yes, I think there is a lot of work being done on incorporating bigrams and trigrams into LDA. What I presented is just the original formulation of LDA. So I believe there is some work being done on that, like you mentioned.
Okay, great. Thanks.
Hi, Chris. Yeah, sorry, go ahead.
No, please.
I just had a quick question. So I was wondering if, I'm aware that you mentioned that you are just starting off, but did you see any work that is done on how coherence score affects the topic models? And so why I'm asking this, the coherence score.
Okay.
Yeah, so I know that a higher coherence score means that there's a better outcome of the topics that we are getting. But when there's a higher coherence score, I also see that the words are repeating over a lot of topics. So do you have any solution for that, or do you know how we can possibly overcome that?
I don't have anything for that right now. Yeah, I'll have to look into that.
Yeah,
sorry about that.
No problem. Thanks.
Yeah, I guess one question I had is, how do you evaluate your model? Or are there heuristics to find the K topics? Like in case of K means clustering, we can have some very rough heuristics and figure out.
I mean, I guess if you have a controlled setting, you can assume a ground truth to the topic models. But in terms of actually evaluating it without ground truth, it's just more, I guess, intuition and looking at it. There might be metrics, but I'm not aware of that.
Right. So in that case, we'd still require human labels and just to understand how topics are. Right. Thanks.
Because ultimately, it's the researcher who gives a label to the topics. So we stare at them, we see words, we try to make sense of them, right? And
correct.
Ultimately, it's gut feeling.
Correct.
I have a quick question too. First, I'm also first time here. It was great. Thank you for that talk, and impressive for a student, really. The one question I have is, so what is a library? Like, if new words are created, like I presume this data command or whatever command picks up the English vocabulary or something, right?
So the library is the all the words, unique words in the documents you're feeding in to the model.
I see. So it's endogenously to the, okay.
Yeah.
Okay, great.
You didn't mention stemming, etc., or maybe I missed it, but that may be a step 0 where you standardize words like doing, do, did into just do.
Yeah.
Right?
That's correct. There's a lot of, I guess, steps you can do beforehand to clean up your documents, if you like, such as stemming. Any other questions?
Yes, I'll just ask one last question.
Yep.
Did you come across any other models which do not have these limitations of LDA?
So I guess this is kind of a plug-in for my supervisor's work, but one of a paper he released last year is a completely alternative formulation of topic modeling using graph theory. I can post the link to that work in the paper, and there's also a Python library as well that implements it. And it overcomes a lot of the limitations here, such as picking K, the number of topics, and then also removes the Dirichlet distribution assumption.
Yeah, okay, cool, thanks.
Any other questions?
Was an excellent talk. You should jump 1 or 2 levels and become a lecturer.
Thank you so much for that.
On that, so we've been discussing with David and Ashani, given that, the last talks were just excellent and we recorded them, and given that both Satya